Welcome to the 2020 Informs OR and Analytics Student Team Competition. I'm delighted to introduce the finalist presentation by the team from Pontificia Universidad Católica de Chile in Chile.
Good morning, members of the committee. We're the team from Pontificia Universidad Católica de Chile, composed by Agustín Chiu, Martín Costabal, Macarena Navarro, Joaquín Osandón, and Sebastián Vázquez. Through the following presentation, we're going to describe our solution method to the production planification problem of the jelly bean manufacturing company. In this presentation, we will describe the buyer manufacturing problem and data, our solution approach and selection, and finally, we will give some insights for the company. To give some context, JBM has to plan its 6-month production of jelly beans to cover the seasonal demand of October. To do this, they have 5 manufacturing locations or plants: Columbus, Detroit, Green Bay, Omaha, and Springfield. Each plant works independently to cover overall demand for each product or SKU, which has a specific color, size, flavor, and package. Consequently, we can consider that each location faces a local demand. Additionally, 1 month prior to production, transportation of raw material is allowed. The production process is as follows. Raw material from RMI beans is differentiated in size in the classifier, in flavor in the pre-finish operation, and in package in the packaging operation. Between processes, there are bins for storage. In this competition, the given task was to design a list of internal work orders in each plant to cover overall demand. This production plan must handle the trade-off between demand coverage, overall cost, and make spans. But what is make span? It is the time at which the last event occurs. In this work, we define 2 classes of make span: the demand make span and the total make span. Demand make span is the time at which the last location finishes producing jelly beans to cover its local demand, as we see in this example where location 2 defines it. On the other hand, total make span is the time at which the last plant finishes producing all of its RMI, which in the example is defined by location 3. We will refer to this problem as the JBM's problem. The assumptions we took to model this problem are the following. Regarding transportation, only 1 trip made by 1 truck is allowed from each location. The transportation cost depends linearly on the quantity transported, and no transfers are allowed after the production period starts. Regarding production, a bin can be filled in any way as long as no contamination occurs, and also bins can be refilled and partially emptied. Regarding the given data, we made the following analysis with the aim to determine its statistical distribution. First, we determined by applying the Agostino test for normality that the processing rates for each location, SKU, and process followed a normal distribution. Then, by applying a t-test and f-test, we determined that it was correct to work with aggregated process rates for each location per size, color, and flavor. For instance, in this example, we can observe the normal fit applied to aggregated processing rates for bagging in Columbus. On the other hand, considering that the maximum coefficient of variation was lower than 23%, we realized that we could include exact methods in our solution framework using average rates. Concerning our solution approach, here we observe the general flowchart, which is composed by 5 processes that I will later describe: production planning, work orders generation, simulation, randomized kick, and calibration. Given the huge dimension of the problem, we decompose it into a 2-stages problem framework. In the first stage, through production planning, we decide how to distribute the initial RMI between locations and assign local demands. Then, through work orders generation, we design internal work orders for each location. In the second stage, we compute the real make spans of the first stage solution via simulation. Each step works with the output of the previous one, as we will later see. As was mentioned, in production planning, we design a production plan. In other words, we assign the initial RMI and a demand to each location by solving a mixed integral program, which considers transportation and capacity constraints and handles the trade-off between cost and make spans. This model just solves the first stage problem. This means that it assigns demand and initial RMI to each location without knowing the consequences on the second stage problem. To estimate this impact, we included a linear function that approximates the production time at each location. I will later point out how to improve this estimation. In work orders generation, we use the NRMI and local demands to design internal work orders for each location. We do this by executing an iterative procedure that follows these rules. We process one color at a time according to a color ranking. To avoid too many setup times, we process one flavor at a time. We use a release batch size for which no size surpasses a PF5 bin capacity. And the remaining material, which is the material produced after covering local demand, is processed by any flavor that the simulation model considers best. The mentioned color ranking sorts colors from lowest to highest generation of leftover material in order to delay its production. In simulation, we compute the real makespans of the first stage solution by executing a discrete event simulation model. This model receives a list of work orders and processes them according to the company's constraints. The model yields makespans, demand coverage, and utilization rates. For filling and emptying bins in pre-finish and packaging operations, we decided to use a more flexible policy than the standard FIFO, which we named push policy. We begin describing our push policy fills a bin. In first place, we search for a bin that has the same SKU we're trying to place in. In case we find a bin, we check if the quantity to be poured fits in it. In case it does, we fill it. Otherwise, we search for another bin. If we don't find such bin, we fill the lowest labeled empty bin. Now, concerning the procedure for emptying bins, by checking bins sorted by ascending quantity level, we follow these rules. First, we search for a work order that matches the selected bin. This is a work order for which the bin has the same SKU and enough quantity to process it. In case there is one, the selected bin is processed according to the work order. Otherwise, we move on to the next bin in queue. If there are remaining bins to select, we move on to the next bin. Otherwise, we process the bin's content as leftover material. At this point, we already obtained a feasible solution to the JPM's problem. However, our two stages decomposition may lead to suboptimal or inefficient solutions. Thus, we propose a process to explore the first stage problems domain and diversify the production plans obtained from production planning. We name this process randomized kick. Here, given a first stage solution, we randomly select one of its RMI transfer, forbid it in the production planning model, and then we re-optimize it. In other words, we seek for a different feasible first stage solution by applying a randomized CAD generation procedure. This process is based on a fix and optimize or fix and release heuristic, which has been proven successful in addressing scheduling and routing problems, and that is also easy to implement. In this example, we observe the transferring of a feasible first stage solution. When randomized kick is applied, we randomly select one transfer, in this case, the one from Green Bay to Detroit, and we forbid it in the next execution of production planning. Then, when executing production planning, we re-optimize and obtain new transfers from Green Bay to Springfield and from Springfield to Detroit, which will lead to a different first stage solution. As I mentioned before, we calibrate the production time function used initially in production planning to gather more information from the second stage problem. This information is included in the first stage problem to obtain better solutions. By solving several times the first and second stage problems, we obtain different processing rates. With this data, we apply linear regressions to calibrate the overall processing times at each location. Then, we use these calibrated parameters to enhance the production time function of production planning. Concerning our solution selection, first, we only studied solutions that cover demand before deadline. Then, we analyzed these solutions regarding overall cost and demand makespan, obtaining a Pareto frontier of efficient solutions. To build this curve, we use average processing rates in the simulation model. As shown in the scatter plot, it is interesting to notice that the variation of cost for efficient solutions along the demand makespan axis is very small. If we zoom in, we observe that 4 efficient solutions were retrieved and are marked with a star. From this step, we mark our selected solution with a red star and the minimum cost solution with a golden star. Our selected solution has a demand make span of 160 days and a total make span of 164 days, which means that there are 16 days remaining before deadline. As we can see, the overall cost of our solution is just 500 higher than the cheapest one found, and its demand make span is almost 6 days lower. Now, with reference to the selected solutions validation, when executing the simulation several times, we obtain a demand make span of 162 days and a total make span of 166 days, which is really close to the performance of the selected solution using average rates. Also, the dispersion of make spans was really small. Therefore, empirically, we confirmed our first intuition that said we could work with average rates without further complications. On the other hand, we achieved a 3% optimality gap with respect to a total make span lower bound defined by a relaxation of the simulation model. In our solution, Detroit was the location that defined production make span and was followed by Columbus. Both of them had their production bottleneck in PFO. With this information, we analyzed the impact on make span of adding extra machines in critical processes. For instance, if we add one PFO machine in Detroit, total make span reduces in approximately 4 days. Additionally, if we add one PFO machine in Columbus, total make span reduces in approximately 6 days. If we also add one PKO machine for bagging in both Detroit and Columbus, total make span reduces in approximately 9 days. Finally, and thinking broad, if we also add one PKO machine for boxing in both locations and manage to double the classifier rate at each location, the company can reduce total make span in approximately 65 days. Regarding transportation, if we add one extra truck to depart from any location, we can reduce cost in more than 18,000 and total make span in 2 days. Finally, we studied the method scalability, for which the mixed integer program in production planning is the critical point. For instances of up to 70 color agents or 6 locations, the model can be solved within 10 minutes. For bigger instances, we recommend a heuristic approach to obtain good solutions in a reasonable execution time. As a conclusion from the presented results, we will mention some insights that we consider useful for the company. First, investing in additional machines for critical locations reduces total make span. For instance, just by investing in one PFO machine for Detroit, a 4-day reduction can be achieved. Also, by investing in one additional truck for transportation, a cost reduction of more than 18,000 and a total make span reduction of 2 days can be achieved. Furthermore, an opportunity to make significant cost and make span reductions comes from investing in Omaha's capacity. This location has the highest throughput, the lowest unit production cost, and represents the second lowest total make span. Therefore, investing in RMI bins for Omaha, together with expanding the truck fleet, may leverage these attributes. By following our push policy, a leftover material reduction and utilization rates increase may be achieved. For instance, in the selected solution, a 97% utilization rate for the system's bottleneck is achieved. Also, we consider worth mentioning that in situations where demand cannot be covered, following our color ranking for generating work orders can help maximizing demand coverage, as it delays leftover material production. Lastly, the obtained lower bound defined by the simulation model relaxation can also be leveraged to design a pruning strategy, which can reduce running times by avoiding redundant executions of the simulation model. This is the end of our presentation. If you have any questions, we will gladly answer them. Thank you very much for your attention.
Very good. Thank you so much. That's a great presentation. And Professor Burge will coordinate some questions from the judges.
Yes, thank you, Macarena, for the excellent presentation. We have a question from Willem.
Thank you. Well, team, I think it was a great presentation. Thank you very much. It was very clear. I have a question. I actually have 2 questions that are related. And this concerns the randomized kick, as you call it, between the second stage and the first stage. I think it was a very interesting idea. My question, the first part of the question is, If you have a first stage solution and then you use, after the second stage, a randomized kick to forbid certain transfers, how do you forbid the process to bounce back and forth, to cycle between two solutions?
Excuse me, can you repeat the question, please?
Yes. So your first stage solution will be evaluated in the second stage, and then you apply this randomized kick. And so you will find a different solution. And if I understood well, you will forbid a transfer to happen based on the second stage of based on the overall solution you got.
Sure.
Now, how do you forbid that you find a solution, you apply a randomized kick, you find another one, you apply again the kick, but then you get back the first solution. And then you basically bounce back and forth between the two solutions and you get cycling.
Perfect. Thank you for your question. We just simply track a list of forbidden transfers in order to not generating the same cut that we generated some iterations before. So we just track the forbidden transfers that we generate, and in that case, the biggest number of iterations that randomized kick can be applied in this case would be 20 seconds, forbidding every one of the transfers.
Thanks. So that would be similar to a taboo list in a local search or a meta heuristic. Okay, great. Now the second part of the question is related to what you said about transferring information from the second stage to the first stage. I'm very intrigued by that. So you say that you can use information from the simulation, the evaluation of the solution, to improve the first stage's solution to find better solutions. Can you give a bit more detail there?
Okay, perfect. So what we do is we iteratively execute the first stage and then the second stage to obtain this real makespans of the first stage solution. And with that data, what we do is to make a moving average to make a sub curve of the production time for each plant, and then what we do is to make a linear regression to estimate a constant that would give us an approximation to the production time at each plant. So we use that information in the initial production planning step to retrieve better information, from what would really be going on in the simulation step.
Interesting. So you keep improving the approximation, the linear approximation that you originally added to the first stage for the simulation.
We do it in a first step. We can call it a calibration phase, and then we run this cycle between first stage, second stage, and randomized kick.
Great. Thanks very much.
Thank you for your questions.
Okay, I have a question about how you use the mean processing times in your overall model. You said in the presentation that the standard deviation or the coefficient of variation was small enough that you could use the mean values. What was that based on an analytical result, or was that based on your simulations?
Yes. What we did was, after running the simulation several times, we realized that I think it's in this one. In this one, we can see that for our selected solution and also in the rest of the solutions, the standard deviation between all the mixpans that we retrieved from the experiments of the simulation was less than 0.5%. So that was a clear result that the deviation of results in the simulation model wasn't large enough to not leverage the mean processing rates and at the exact method. I mean the production planning step. We also we use this calibration and randomized kick steps or methods to address also the case in which maybe that deviation was too large or was too big. In that case, randomized kit would be a major player in this case. The calibration wouldn't be that precise, and we would maybe spend or would like to spend more time searching for the problem's domain instead of calibrating.
Okay, are there any other questions from judges? If not, then again, I want to thank you for your presentation. Thank you for spending time with us, and I'll turn it back to Terry.